Good morning, good afternoon, good evening, everyone, wherever you might be. Well, this is the last lecture of the school, and we will end it with knot theory. Why not? Again, it is my honor and pleasure to introduce the speaker, my friend and colleague from New York, Buffalo, State University of New York, Adam Sikora. He did his PhD in the year 2000 at the University of Maryland, College Park. And I cannot resist to tell you a funny story that he had with his PhD. Well, you know, when you get a PhD, it's Doctor of Philosophy. And once, for some formalities, he was accused that he's not qualified to go and teach mathematics because he's Doctor of Philosophy, not mathematics. So you have to be very careful when you get your PhD. Why don't you get your MD, mathematics? Anyway, jokes aside, Adam's main interest is in interactions between topology, algebra, and number theory, modular spaces of representations, and very quantization. So, welcome to knot theory. Without any further ado, Adam, the floor is yours. I stop sharing, you start sharing, and we rock and roll.
Thank you. Thank you, Piotr, for inviting me and for this wonderful introduction. Let me do the sharing here. This is.
We can see it, all right?
All right. Sorry, guys. I'm just adjusting here the frame. All right. I hope you guys can see the first slide. Yeah, so thank you again for the introduction. Thank you, Piotr, for inviting me to this workshop. I wish I could be in person with all of you, but given the reality of COVID and the fact that I live on different continent, I guess we'll settle on a virtual talk. And in case you wonder where is Buffalo, well, it is 20 miles from Niagara Falls, which you can see here on the picture. And 1 second, technical difficulty trying to figure out how to do, how to advance the slide.
Yeah.
Oh. Somehow, I think Zoom is blocking my. Well, I think we'll just do this.
Yeah.
All right. So what's a knot? A knot is an embedding of a circle into three-dimensional space. We'll talk about knots and about links. And those are embeddings of collections of circles into three-dimensional space. And they will be considered up to isotopy. That is continuous deformations, which do not allow for a link or part of it to pass through itself. So you cannot pass one piece of string through another. And equivalently, instead of R3, one can consider three-dimensional sphere. So the theory is the same because they only differ by 1 point at infinity. So, well, here you see on the side some knots. This is called the unknot. This is called the trefoil. This is called a figure 8 knot because it has this 8 here in it. And this is a link. And this is a link of two components called, in fact, the simplest non-trivial link called the Hopf link. And so, by the way, a knot can be thought as a link of one component. And knot theory intrigued people and inspired art, at least since Brown's age. And of course, it was of great importance in practical applications like sailing. And here is an example of an ancient Roman mosaic. And you can see Hopf link here. And this is a decorative element on a Chinese pot from the Ming era, about 400 years AD, of the Common Era. And knots inspired scientists throughout the ages. Here you see a page from Gauss's famous mathematician's Gauss, a notebook from the end of 18th century. And then the modern roots of knot theory is, perhaps start with Lord Kelvin. This is the guy who, after whom we have a temperature scale named. And in the mid-19th century, scientists were wondering about speculating about the nature of different chemical elements. And so he proposed a theory in which different atoms are knotted tubes of ether called vortices, and they correspond to different knots. And in this theory, chemical elements, chemical molecules correspond to links built of different knots, different atoms. And well, the theory was, of course, bonkers, but it led to attempts to classify all knots and links. And to do that, it's convenient to represent them by two-dimensional diagrams. So here you see such diagrams. Again, this is the unknot. You have three diagrams here with number 6. That means that there are 3 different knots with diagrams with 6 crossings, and they are just named 6.1, 6.2, 6.3. And well, so of course, every knot and every link has different diagrammatic representations. And there's a theorem due to German mathematician Meister, which says that any two such diagrams, the diagrammatic representations of a link, are related by the following moves. This is called the first Meister move. So we just undo this little loop here, or create it. Any two pieces of string, of course, can be pulled apart like here, and all created. So you can create 2 crossings like that, or like that. And then you have the third Meister move. Now, before I continue, perhaps a disclaimer that this is an informal introductory talk, so some statements will not be completely precise or accurate. And also, I'm going to mention in this talk a large number of topics in higher mathematics. And so I had to make difficult choices. What background which is necessary, I can assume that you guys have, and I will skip that, which may be hard on some of you. But then I will be introducing some other background, which may be obvious to some other of you, and perhaps boring, especially for professional mathematicians in the audience. So I just hope for your patience, and I apologize to everyone in advance. So with that, let's continue. So when you have 2 diagrams proving that they represent the same link, usually involves showing a sequence of other Meister moves, relating them, and that's not always obvious. Those moves are not always obvious. So for example, let's just, without looking down, without cheating, let's just look at this specific diagram. Well, can you guess if it can be simplified? Well, it doesn't look like it can be simplified, but it can. And in fact, the first move towards simplification is pulling this arc underneath and like that. So you have to create 2 extra crossings before we can simplify it, because then the idea is that we are going to, I don't know if this is visible. Let's see, oh, I can make it larger. Then the idea is that we're going to pull this string underneath like that. And well, then with the further simplification moves. And so by starting by adding those 2 extra crossings and doing those simplification moves, actually we're able to untie this knot completely. So this is not obvious, at least to me, but this diagram represents the unknot. So proving, so classically the main problem in knot theory is determining whether 2 diagrams represent the same knot, or whether basically 2 presentations of the same knot or link are isotopic to each other. And so proving that they are usually is done by showing a sequence of Meister moves relating their diagrams. Now, proving that 2 diagrams are not equivalent is harder, because one would have to establish that there's no sequence of Meister moves relating them. That's pretty hard. So it's usually done by defining and considering certain invariants of links. And these are functions on link diagrams into usually some algebraic objects, which are preserved by Meister moves. All right, the simplest such example, of course, would be the number of components of L. So the Hopf link cannot be isotopic to trefoil because the number of components of a link is an invariant. And then with advent of algebraic topology at the beginning of 20th century, people started using tools of algebraic topology to construct such invariants. And of course, the simplest topological invariant of a link is its complement in R3. So this is a certain topological space considered up to homomorphism. And there is a famous theorem of Gordon and Lucke, which says that this complement of a link, well, the complement of a knot in this case, distinguishes knot up to its mirror image. So a mirror image is when you take a diagram and you just flip all the crossings to the opposite crossings, and you get a mirror image. That is actually not true for links. In any event, so this leads to a problem of distinguishing non-homomorphic topological spaces, at least for knots. And a basic tool for that in algebraic topology is the fundamental group, denoted like that, by 1 of Y, of topological space Y, which for connected space is just the space of the set of all closed loops in Y up to homotopy. And those loops are supposed to all have certain base point in Y, and the homotopy preserves the base point. And so, for example, you have here 2 loops A and B in the torus, the surface of a donut. And those loops, such loops form a group. Well, they must be, those loops must be oriented. So there's no orientation on A and B, but when they are oriented, then you can consider composition of those 2 loops. And AB, well, means you first go around A and then around B, and you get a loop like this. So it's easy to prove that this is a group. So fundamental group, the fundamental group of oh, let me extend the screen here if I can. All right, a fundamental group. In fact, one can prove that distinguishes all nodes, again, up to mirror image. And in fact, for any topological space, it's easy to describe its fundamental group by generators and relations. However, unfortunately, the isomorphism problem in group theory is unsolvable in general, which means that given two groups by their generators and the relations, there is no general algorithm to decide whether they are isomorphic or not. So, yes.
So, is it possible to classify all possible groups which appear in this way as a fundamental group of a complement of a knot? Is it known?
Well, I think all relies on the precise definition of the word classify. So there is no simple definition. You cannot do it like using few adjectives about groups. But maybe there's some cumbersome way to do it. I would have to think about that. Yeah.
So, for example, every finitely presented group is a fundamental group of 4 manifold. There is such
That's correct.
theorem. Yes. So I'm wondering how this situation looks like in this case, where we consider a complement of a.
Well, so there is no such nice theorem or neat theorem for knot groups. So these are called knot groups. I mean, what we know is that a stabilization of this group, which is first homology of the complement of a knot or a link, is Z to power the number of components of L. But as I said, there's no, at least coming to my mind, and I don't believe there is one like a nice, clean characterization of what groups can you get.
Okay, thank you. But if I understood correctly, after taking a quotient with the commutator subgroup, you get always a 3 abelian, yes?
Correct, yes.
Okay, thank you. Thank you. So this is nice.
Yeah, so this is a very good question because this already clears, covers already the question of homology groups, which are also another type of basic topological algebraic topology invariants of spaces. They are very weak invariants of links. They just determine the number of components. And this is in principle, strong invariant if you know how to distinguish different finitely represented groups. Nonetheless, algebraic topology provides other useful invariants like the Alexander polynomial of a link, which is nice, but not entirely satisfactory for the purpose of classifying nodes or links. All right, so before I continue, let me address a certain potential elephant in the room. And that's a question, why should we really care about nodes? In general, I guess it's a controversial question in mathematics. The purists will say that nodes and links exist, and that's a good enough reason to study them. But pragmatists, for lack of a better word, may say that an importance of a theory in math is based on certain criteria. For example, what are the applications of that theory to other sciences, or practical applications, or how is it connected with other areas of mathematics? And so it turns out that knot theory does surprisingly well by these criteria. And it has significant connections with practically all areas of math and strong connections to advanced physics. Not to mention, of course, sailing or other or mountain climbing.
Adam, Adam, can you hear me?
Yep.
Can I ask you a stupid question? I'm looking at this sentence after theorem of Gordon and Luke. Yeah. And what do you mean by problem of distinguishing non-homeomorphic topological space? If they are non-homeomorphic, they are different, so they are distinguished.
Well, you know, I can draw you to topological spaces, and I can ask you, are they homomorphic?
Mm-hmm. Okay, so you want to decide whether or not they are homeomorphic. Okay.
Correct. Yes.
Okay. Okay. Thanks.
And for a knot complement, that's enough to determine whether two knots are isotopic by that theorem. All right. So I was talking about the applications, even though it may look like some exotic kind of mathematics, piece of mathematics. Actually, it has many applications. So let's talk about them. So first of all, the first application is to topology. So one of the main problems in topology is a classification of manifolds. And so what is a manifold? It's an n-dimensional manifold. It's a topological spaces M, which locally looks like Rn. Yes, so connected one manifolds are R, infinite line, and a circle. Two-dimensional manifolds are just surfaces. And so you have a sphere. They're classified by, well, at least the compact ones. The closed ones are classified in the following manner. You have a sphere, you have a torus, a surface of a donut. You can have a donut with 2 holes, with 3 holes, and so on. And then there is an infinite family of non-orientable surfaces. And then just to classify non-closed surfaces, well, you can just remove open holes from those surfaces, and then you have surfaces with boundary.
By
well,
P2,
actually,
Adam, by P2 you mean real projective space, real projective
yes.
plane. Okay.
Yes, and this is a picture of Klein bottle. So this is a well understood topic, and then of course people try to understand classification of 3-dimensional manifolds, and that's way more challenging and interesting, of course. Classification of 3-dimensional, 4-dimensional manifolds. You know, we live in you can think that we live in 3-dimensional space. So the cosmos, the universe is 3-dimensional space, but of course with time is 4-dimensional space. So it's some sort of manifold, possibly with I guess with singularities being black holes, but ignoring that, it's a manifold. Anyway, so there was a lot of effort put in recent decades in understanding, classifying 3-dimensional spaces, with major contributions from famous mathematicians like Bill Thurston's and Grigori Perelman, who solved the famous Poincare conjecture. And so by now we have pretty good understanding of 3-dimensional manifolds, although I don't think we have a classification per se. And I can tell you a crucial tool in analyzing 3-dimensional manifolds is a surgery. So what's a surgery? Well, on a surface, surgery consists of cutting a surface around the loop, and like I try to depict in this picture here, the red loop, and gluing and filling it with a disk, and it results in a new surface. The surgery in the context of 3-dimensional manifold consists of taking a link in that manifold. So now we're talking about embedding of circles into M, and taking a solid neighborhood of a knot or a link and removing it. And by removing it, you obtain a manifold with boundary torus. And well, you obtain a solid torus. And then there's a lot of ways, different ways to glue it back, because you do it by gluing back the boundary of a solid torus, which is a torus, with the torus boundary of the manifold, and there is many different homomorphisms of torus to itself, or from one torus to another. Different homomorphisms will produce different topological spaces. This is called serger on a knot. It can be done on a link. It's a very useful tool because, for example, with this technique, with this method, you can, you can serger any manifold into any other manifold if they are connected. And if they have the same boundary. Well, here, I guess I assume there's no boundary. So, so that's the first application to study three-dimensional manifolds. Then there are relations to physics, which will take more time, so I will discuss them in a moment. Then there are relations to number theory. Those relations were discovered initially by Mumford in the 1960s and then pursued by Barry Meister and by others, and currently by Morishita. And so it's a theory which postulates that a three-dimensional manifold is like a number field, which means it's an extension of rational numbers of finite degree. For example, Q adjoint square root of 2. And according to this theory, links in a manifold are like ideals in the rings of algebraic integers. So for this number field, the ring of algebraic integers is Z adjoint square root of 2. And well, knots, according to this analogy, correspond to prime ideals. In particular, a three-dimensional sphere, the simplest three-dimensional manifold, corresponds to rational numbers. Links will correspond to ideals in Z. And, you know, all ideals in Z are cyclic. And so they correspond to natural numbers, or to 0, I guess. And knots correspond to prime numbers. Well, prime ideals, according to this, from this point of view, correspond to prime numbers. All right, so knots are like primes. So I know this may look bonkers, but or may look silly or very simplistic, but I can assure you it's not. It's a very serious theory, and basically it has this whole dictionary relating topological terms in knot theory to on three-dimensional topology in general, to notions in number theory, and the origin of these analogies is not understood, but they go quite deep. And basically what it means is that there are certain statements in topology where, using this dictionary, you can translate them into true statements in number theory. And in fact, I wrote a paper on the subject as well, exploring some of such analogies between equivariant cohomology, well, between group actions on manifolds, and equivariant cohomologies related to those group actions, and some Idle class field theory on the other side, on number theory side.
Excuse me, Adam, can I have a question?
Sure.
Is it easy, or even maybe you could intuitively say why Q corresponds to S3? Because it's why this field or not some other?
Okay, so accepting this analogy in general, why S3 to Q? Well, you know, the basic fact is that this is the simplest three-dimensional manifold of sorts, and this is the basic number field. But I'm going to maybe actually respond to it with the next line. So in particular, in this analogy, homology group of M corresponds to the class group of K. So if what is a class group? Well, class group is a finite group which measures to what extent this ring of algebraic integers fails to be unique factorization domain, or principal ideal domain, which happens to be the same. So for example, for S3, this is trivial, and of course Z is a principal ideal domain. So so that's one reason why we have this analogy. Well, maybe it's not a strong reason. And then, according to this theory, branch coverings corresponds to extensions of number fields. And the way links in M are lifting to links in M tilde correspond to extensions of ideals. Okay, so, in particular, every three-dimensional manifold is a branch cover over Q. And this seems like a good model or good analogy to saying that, of course, every number field is an extension. Sorry, what did I say? Every branch cover is every manifold is a branch cover of S3. And this is analogous to the fact that every number field is an extension of Q. Of course, there's lots of issues with this analogy. It's easy to poke holes in this, obviously, such extension from Q to K is unique, and branch covers are not necessarily unique, and so on. So it's easy to find reasons why this is not a perfect analogy, and it's not. But it's still amazing how deep it goes. And to give you a more sophisticated reason why we have this analogy is that in number fields, there's a cohomology theory for number fields called étale cohomology groups, and there is a certain sheaf with certain sheaf coefficients. Étale cohomology groups look rings of algebraic integers as three-dimensional objects. And in fact, objects which satisfy a certain version of Poincare duality called Artin-Verdier duality. And there is even a paper by Kapranov, which claims that this analogy can be extended, and that quantum field theory on topological side is like Lagrange's program in number theory. Well, of course, you can ask, what's quantum field theory doing here with knots and links? Well, this goes to those connections into physics, which we're going to discuss in a moment. And
may I have a question?
Yes, sure.
So about this last correspondence, I thought that the Lagrange program itself is some kind of big picture correspondence between two different branches of mathematics. Between on the one side there is a representation theory, and on the other side there are some deep connection with number theoretic labor.
Yeah.
So this correspondence shows that in fact all these two should be somehow related to quantum field theory. Yes.
Well, so Lagrange program is a correspondence, and quantum field theory can be also considered as correspondence. Like say, let's take topological quantum field theory. It's correspondence between surfaces and certain algebraic objects, and three-dimensional manifolds and certain algebraic objects. So yes, it's a correspondence between correspondences.
Okay, thank you.
And so maybe now on the lighter side, so a DNA strand can form a knotted loop. Here is a picture, a beautiful picture of some knot like that. And I even heard a claim, don't quote me on this, but I heard a claim that if a cell has too much, the DNA strands, the DNA has too much knotting in a cell, then it shortens the life of a cell. So try not to knot your DNA too much if you can. So knots appear in nature in this way, but the connection with knot theory here is in fact deeper, because to study the knottings of DNA, I guess one takes a solution with DNA strands and then add some enzyme, and that enzyme will lead to recombination of DNA, which may change the knotting of it. And so then we see the recombined DNA And this leads to a problem which can be considered a knot theory problem, trying to understand, knowing how the action of the enzyme, the properties of the enzyme, and seeing the final result of the recombination, try to figure out the original knotting of the DNA strand. So there are some topologists like David Summers and others and his collaborators who wrote papers about that. All right, so moving on. So before we continue with physics and other topics, let me quickly introduce braids. So a braid on n strand is a family of n arcs going in some direction, say going down, like here you see n strands, 4 strands going down and twisting around each other. And n braids form a group with the identity being the trivial branch, so just n strands going down without any crossings. And the group operation, of course, is composition. And it's not difficult to think, if you think about it for a little bit, it will not be difficult to see that every element indeed has its inverse. Like here I have this crossing of 2 strands, and I could now compose it with opposite crossing, and that would undo this crossing. Yes, I can then compose it with opposite to this crossing, and then I can add an additional braid here on the bottom, which will undo all the crossings you see. So there's a natural homomorphism from the braid group to the permutation group, where you forget about the middle part, the braiding. You just trace where the first strand goes. It goes to the second endpoint, and the second beginning point goes to the first endpoint, and the third one goes to the third, and fourth goes to fourth. So you get a permutation of 4 points. And now, when you have a braid, so the braid here, for example, between those dashed lines, then you can always close the braid and you get a link. And one can prove, it's an old theorem I think of Markov, which says that every link can be obtained in this way. And in fact, you can study knot theory, so you can study links through braids, through those presentations. So now let me tell you about some applications of braids in particular. So going back to analogies between topology and number theory, there is this mysterious, complicated to define group called Grothendieck-Teichmuller group, introduced by Drinfeld. And so, as I said, it's complicated. I'm not going to define it, but the definition, at least one definition, involves braids. It's related to braids. And what Drinfeld proved is that this group contains the absolute Galois group of Q. And in fact, for what we know, it may be an isomorphism, which would be quite amazing if it was, because arguably this absolute Galois group is the most important object in number theory, understanding this group. Yes, so in particular, we have, say, a famous inverse Galois problem, which asks, is it true that every finite group is an image, homomorphic image of this group? So moving on, a second application of braids or connection of braids to other areas of mathematics. Braid group is the general group, GLN group, over the ring of polynomials over the field of one element. So this may sound crazy if you never heard of that, but you know, there are many objects, algebraic objects you can consider over finite fields. So this is my notation for a finite field of P2N elements. There are vector spaces, matrix groups, and so on. And mathematicians, I think initially Japanese mathematicians, I forgot the names, specific names, they realized that there are certain combinatorial objects which correspond to such vector spaces and matrix group and so on, which are not really associated with any field. And, or more precisely, they started hypothesizing about this mysterious field F1, and they developed this this theory of properties of F1. Of course, there is no, you know, on the nose. If you open the definition of what a field is, of course, there is no field of one element. But there's at least one paper I saw which tried to make the notion of F1 precise. In any event, it's postulated that the general linear group over F1 is just a permutation group, and the general linear group over polynomials in X over F1 is the braid group. And of course, evaluation of X at 0, well, will define a map from this general group to this general group, general linear group, and this corresponds to the homomorphism we discussed from the braid group to the symmetric group Sn. Next application or relation of braids is in set theory. Set theorists these days, they study things like certain large cardinals, properties of large cardinal numbers, and their independence of axioms, of known Zermelo-Frankel axioms. And I will not go into the details, but those things are related to braid groups. And then finally, braid groups are used in cryptography. And in part, that relies on the fact that given two n braids, beta and beta prime, it's deciding whether they are conjugate, and finding a conjugator alpha, so such that this identity holds, is hard. And however, verifying that this is true, given alpha, it's fast and easy.
It's like factorization into prime numbers, right?
Yeah, something like that, exactly. Okay. So, well, so now in order to relate knot theory to physics, we should talk about John's polynomial, but I am checking my time here, and I think it's good time to stop for now.
Okay, so let's have a coffee break. However, before we do it, will you elaborate a little bit between the link, I'm saying it as an English word and a mathematical term, between a link that we have between braids and quantum groups? Hello?
Yes, so okay, so I was planning to talk about quantum groups later on, yes, there is such a thing as a quantum group indeed, and people study its representations, and every representation of a quantum group defines representation of the braid group. And this is done through, well, this is related to Young-Baxter equation, if you heard of it. I don't know if that's what you're asking specifically.
Yeah, exactly.
Oh, okay.
Yes. Okay. So yeah, thank you so much. So let's have a 15-minute break, and we resume at 4 p.m. sharp.
All right.
I will pause the recording. Okay, recording in progress. Your talk is in progress. Go ahead.
All right. Thank you. So going back to this question, which I was asked about knot groups. So fundamental groups of knot complements. Now I remember there's a theorem of Stallings, which says that there is no algorithm to determine whether a given finitely presented group is a knot group, is of this form. So that's one clarification for the previous discussion. Now, moving on. So in order to relate knot theory to physics, when you talk about the Jones polynomial, so as I mentioned already earlier, algebraic topology gave us some invariance of links, most notably the Alexander polynomial, which was already invented or discovered in 1920s, and there was some progress in knot theory since then. After that, but the next true revolution in knot theory really came with the Jones polynomial in 1984. And so he proved that you can associate to every oriented link a polynomial, a round polynomial in this variable, such that this polynomial called Jones polynomial is 1 for the unknot, and it satisfies the following skein relation. And what it means is that if you have 3 different diagrams, which are actually identical, link diagrams, which are identical everywhere except at one spot, and the first link in that spot has this crossing, this is a positive crossing, the second link has negative crossing, and the third one has no crossing at all, has those 2 arcs like that, then those 3 diagrams, the Jones polynomials of those 3 diagrams are related by this equation. And then the Jones's construction was quite complicated, quite advanced. In fact, the motivation for his construction came from the study of von Neumann algebras. So I could have mentioned also that in relations to knot theory.
Sorry, what is the reason for this 1/2 in an exponent? Why just not consider?
It's just a traditional. It's just a traditional notation. So we could replace.
So
we
convention,
could,
yes, some kind of convention. Okay.
That's right. Yeah.
Okay. Thank you.
And so, and then soon afterwards, Lou Kaufman invented an equivalent invariant. However, his invariant is for framed links in R3, which are unoriented. And the frame link is just embedding not just of circles, but of annuli into R3. So you can think of them as bands while forming annuli, and you embed it into R3. And so in order to draw those things on, we use the Blackboard framing usually. I guess we don't really use much blackboards these days in mathematics, but I'm glad you guys have blackboards there in Mendeleevo. Anyway, so what is Blackboard framing? Well, it's a framing which is always parallel to the page or to this computer screen. All right, so in particular, this king here cannot be untied, cannot be simplified, because then it will have a twist, a double twist when you try to do it. All right, so the theorem of Kaufman says that there exists a unit bracket function on all framed links, unoriented framed links, into Laurent polynomials in A, such that whenever you have 3 diagrams, where again identical everywhere except at one place when there's a crossing, this moving and this moving, then we have the following skein relation. This is called skein relation. And the second property it has is that you have a link with unlinked trivial component, then you can remove it and replace it by this constant. This constant looks unintuitive, but in fact, this is the only possible constant consistent with this skein relation. And the proof that such construction, such function is unique, if it exists, it's obvious, because if you take any framed link like this trefoil here, then you can resolve all the crossings by this relation. And at the end, if you resolve all the crossings, then you just have collections of trivial loops. Yes, like this is, there are 2 loops here, and this is a single loop here, and you can compute their value by this relation. So for that, and then checking that invariance under the Meister moves actually is quite simple, and yeah, it's actually very elementary. Once you realize that such a thing exists, proving that it does what it does is very simple. So for example, for the trefoil, we get this value, which tells us immediately that trefoil cannot be unknotted, because the value of the unknot is minus a squared minus a to minus second power.
Sorry, I'm slightly confused by the use of word bracket. So this already means something, that we pose some axioms, or this is just one, this is a function of one variable, yes? It's not some sort of Lie algebra bracket, yes?
No, yeah, it's a name of this specific function, and we draw it by, well, we draw it by drawing a bracket. So a bracket.
Yes, but in the statement of the theorem, the first part, there is unique bracket, means at this moment means nothing. Yes,
I see. Okay, yes, very good. So there is a unique function. This is a mental shortcut. It means this unique function, which is called a bracket.
Okay,
Kaufman bracket.
Thank you.
And it's related to John's polynomial by renormalization. So if you have an oriented link, then you can consider it with arbitrary framing. You take the bracket. And no, sorry, when I say that, sorry, so you take oriented link diagram in a plane or on Blackboard, and then you take its bracket, and then you multiply it by this factor where W is so-called right of the diagram, which is just the sum of crossings of L, signs of crossings of L. Again, this is positive crossing, this is a negative crossing. And after this randomization and change of variables, you will get the John's polynomial. All right, so one can find the John's polynomial is not an ideal invariant of links or knots. One can find pairs of different links with the same John's polynomial. However, we don't know such examples where one of them is the unknot. And in fact, John's formulated this conjecture, the John's conjecture, which says that it is impossible if John's polynomial of k is 1, then k must be the unknot. And in fact, there was an attempt by the AMS, American Mathematical Society, to compose a list of problems for 21st century in the spirit of Hilbert problems for the 20th century. And so this is one of the problems which John's proposed for 21st century for us to solve. So following that, my student and I, well, we verify this conjecture computationally, at least up to 24 crossing diagrams. And that involved testing, as you can see, more than 10 to the 13th of knot diagrams. I don't even know the word for that kind of numeral. On a supercomputer here at SUNY Buffalo. That requires a lot of optimizations to actually reduce it, this problem to only considering this many knot diagrams. And then it's a challenging problem to compute the John's polynomials or the Kaufman brackets, because as you can see, the simplest way is exponential in number of crossings. So we have 30,000 lines of code for that, various optimizations. And by the way, I should mention that this is a version of this conjecture for links is not true. So Tisselweiss and Kaufman found examples of links which are non-trivial, which have the same John's as the trivial link. And well, let me mention this. Let me end this slide by mentioning that there are many other open questions about John's polynomial, because it's quite a mysterious, really, quantity. And for example, we don't know what polynomials appear as values of the John's polynomial. All right, so now let's talk about connections to physics. So a few years after the Jones polynomial was invented or discovered, Witten, perhaps the most famous contemporary physicist, famous for his important contributions to string theory, in particular, published a paper in which he gave a physical interpretation of the Jones polynomial. So this will be fairly advanced, but I'm not going to explain all the details here. But the good thing is that this is not absolutely necessary for the continuation of the talk. Nonetheless, I think it's useful to discuss this a little bit. So what Witten discovered is that, or claim is that for any Lie group G, so a Lie group is a matrix group. Well, for us would be just a matrix group, which also happens to be a manifold, like GLN or SUN. So for any such group, and for any positive integer k, and for any link L in a three-dimensional manifold M, Witten claims there is an invariant. So I guess I should say there is an invariant such that for any link L and manifold M, this invariant associates to it a complex number given by a certain path integral. And the path integral will be over a certain connections A on M. And I'm not going to define them here. This is just too advanced, but for people who know a little bit about gauge theory, what happens here one fixes a principal G bundle over M and considers connections on this bundle. And given a connection, which happens to be one form, you can consider this free form called Chern-Simons form, and then integrate it, and one can associate with it a number, a real number, defined up to 2 pi z. And then one puts it here in the exponent and integrates this over all connections. And then there's certain terms here called Wilson loops, which one puts here for all the components of L. Okay, so let's
Sorry,
have this.
may I ask?
Yeah.
Something. So what is mathematical status of this integral? This is well defined mathematically?
Yeah,
I'm about something like integrating over infinite dimensional.
Yes, exactly it is. I was about to say that. So that's why this theorem is really in quotation marks, because for us mathematicians, this is not really precisely defined, because in fact, all connections like this, they form an infinite dimensional affine space. And in order to do an integration, we would need to have some measure. There is no natural measure to consider here. So nonetheless, path integrals are extremely important in physics. So this, what you can consider, this construction would go into something called Chern-Simons field theory. And physicists use them in other field theories. They are very important in the standard model of particle physics, for example. And physicists, they, even though it's ill-defined, physicists have certain experience with dealing with those objects, know what kind of operations they can do, and without getting into trouble. But
so the link is hidden where in this definition of CIs, yes?
Well, that's right, yes. Yep.
Okay, in the W of CIs.
That's
okay,
right.
I see.
And basically, it's a trace of certain holonomy given by the connection along the component C.
Okay, thank you.
So, and so, this is quite fascinating because, by the way, because we are used to the fact that math is applied in physics, but here is an example where physics is applied to math, and we obtain a very interesting physical intuition. Well, the physical intuition provides some insights into mathematics, and the various there are certain conjectures inspired by this claim, rigorous conjectures inspired by this claim. Actually, to talk about them, so I need to talk about Reshetik into Rayev. But first of all, let me mention that several people I mentioned here in the talk got Fields medals for their work. I mentioned Rindfield, he got Fields medal for his work. Then Jones, then Witten for his contributions to mathematics, perhaps as the only physicist ever. And in an event, so
but Adam, we recently retaliated. There is a mathematician with a Nobel Prize, so now.
That's right. That's right. Yes. Oh, that's a good point. And I should have related this to knot theory, but I forgot about that. All right. So soon afterwards, two mathematicians, Reshetik and Turayev, indeed try to define rigorously an object of this sort, as Witten postulated or defined physically. And that led them to the invention of topological quantum field theory, called simply TQFT, which associates to, it's a theory which associates to each surface a vector space. And okay, so for that, as input, we need two things. We need a Lie group G, and we need an input, again, then non-negative integer natural number K. And so we get a vector space, finite dimensional vector space for each surface. And if you have a link in a manifold M, that there defined a vector in the vector space associated with the bundle of M, well, associated with also this link and M. And in particular, if one can define this this vector space for the empty surface, so it's allowed to use empty set here, and this is then complex, just complex numbers, one-dimensional vector space. So you get a scalar. So in particular, for closed manifolds with a link in it, you get a complex number.
Sorry for interrupting so often.
No worries.
So M is fixed, yes, M is fixed, and we think of M as the D manifold in which we live, yes?
No, I don't like, no, M is not, well, it depends what you mean by fixed. It's for
quantum field
this
theory corresponding to M.
No, well, I would prefer to say, well, I guess you can say that. I would prefer to say that you fix G and K, and then for every M and for every L, you have this invariant.
Okay, G is Lie group, and we should think about it as some gauge group, yes?
Yes.
Something like SU2, for example.
Correct, yes.
Okay, and K is just an integer?
Yes, just natural number, like here.
Okay. Okay, thank you.
Yeah, and well, the construction of this theory, and okay, so this goes back to your question too about Kapranov. Yes, so Kapranov, you see, you have some sort of, you can say, duality or functor between surfaces and three-dimensional manifolds and links to some algebraic objects, and so Kapranov was comparing that to Langland's program, which are also some correspondences. In any event, so the construction of that is it's rather time-consuming and non-elementary, and it relies on this concept of a quantum group, which I'm not going to define, but maybe I'll just mention that, yes, for each semi-simple Lie group, at least, you can define those two quantum groups: the deformation of the universal envelopic algebra of its Lie algebra, and the formation of the algebra of functions on the group. They are dual to each other, so they will make an appearance later on. And in particular for SU2, which is the simplest non-trivial Lie group, you may say. And for any K, this turns out to be a version of the Jones polynomial at root of unity, at Q being root of unity. All right. So the construction of the Bershitek into Rai theta QFT is quite complicated. Oh, so I guess I should have finished that. So why do we consider those quantum groups? Oh, I wrote here because then you can study the representations. Piotr asked me a very good question. Any such representation leads to a representation of the braid group, and through braids, for example, you can try to define invariants of links. And so this is one way to try to at least partially define this theory. In any event, I want to now go a different way, use a different approach to define invariants of links in three manifolds, which is much simpler, at least conceptually. So fix a commutative ring R, because there's no reason to be specific, and just assume and fix an invertible element in R. So for example, just Laurent polynomials in this variable A. Now, for any three-dimensional manifold, the Skane model of M is going to be the space of formal linear combinations of links in M. And so this is an infinite dimensional space, even if you consider links up to isotopy. And you quotient it by the Skane relations you saw for the Kaufman bracket. So you say that this link is equal A to this link plus A inverse times this link. The meaning of it is as before, three links which are identical except at one spot. And then L union unknot is equal this much. All right, so it's kind of hard to wrap your mind around it because it's a quotient of infinite dimensional R module by an infinite dimensional submodule. But it sort of right away, by abstract nonsense, gives us invariant of links in M, because for any link, you can consider a class of link. L, after all, is an element here in the Skane module. So you have an invariant. And then you can prove, it's not difficult to prove, that the Skane module of R3 is cyclic, generated by the empty link. So for this theory, it's useful to assume that empty set is a link of zero components, just formally added there. All right, so and so the bracket, the Kaufman bracket will, okay, so this means, of course, that every link corresponds to some scalar R, and this correspondence is really the Kaufman bracket, you know, is for this ring, especially for this ring at least. So this is really a reformulation of theorem of Kaufman. And well, proving it's cyclic is not difficult because for any link in R3, of course, you can resolve all its crossings. So eliminate trivial loops, and you will end up with a scalar multiple of the empty set. So I'm going to study those Skane modules. And frankly, I am not going to do it because they define invariants of links, but because they lead to a very rich theory with various connections to some other advanced topics in mathematics, and which I will try to explain in the remaining time. Perhaps I should also add here, by the way, that these Skane models were first introduced by Pshititsky and by Józef Pshititsky and by Vladimir Turayev. All right, so yeah, so let's talk about their properties. So first of all, let's take A to be plus minus 1 in some ring. So then I can rewrite this Skane relation in this way. This will be plus or minus depending on A. But notice that, you know, if I rotate those pictures 90 degrees, then I get the same Skane, I get the same element. They just exchange their places. So in other words, it means that this crossing is this crossing, assuming A equal plus minus 1. What does that mean? Well, it means that really its utility as an invariant perhaps diminishes here because you can just freely change crossings well, you can change crossings in links, but there's a positive of that. And that is that now we can define a product of two links as their union. And in general, the problem is there is no canonical way to put two links in M together. You know, if you're not in R3, if you're in R3, you can sort of say, well, one is on one side, another is on the other side. But if you are saying S1 cross in three-dimensional torus, S1 cross S1 cross S1, there is no such thing as left side or right side, or there's not even notion of above and below. But however, if you can change crossings, then it doesn't matter. You can just take any disjoint union of them, and they're all equivalent through this move. So what it means is that you get, through this multiplication, the scale model becomes an R algebra, commutative R algebra. And so we can ask, what kind of commutative R algebra do we get for every three-dimensional manifold? All right, so this leads us to the notion of character varieties, but let's start from the beginning. I mentioned to you guys that there is no general algorithm for distinguishing two groups given by generators and relations. So that means that in practice, we often try to distinguish two groups like that by studying the representations into another group, usually a matrix group. And so, for example, you try to prove that two groups are different by saying, well, this group has homomorphism into maybe SL2C, and this one doesn't have any non-trivial homomorphism into SL2C. That would show that they are different. And in general, this leads to a considering of all representations of gamma into SL2C. All right, and it's a very large set often, and the SL2C acts on the set by conjugation. And so mathematics, we often identify conjugate representations. So let's consider the quotient of this space by this action. And this is called the SL2C character variety of gamma. And of course, everything I did here can be done for any nice matrix group. And so this is just SL2C here is just for simplicity. So now I claim that this is naturally an algebraic set, which means, what does that mean? Well, it means it's a subset of some affine space, can be of large dimension, which is a solution of certain polynomial equations. Okay, and so that's not an easy claim intuitively to justify. So let's just look at an example. Let's say gamma is a free group on two elements. Then I claim the following, that such representations up to conjugacy are determined by three complex numbers, by trace of row of A, trace of row of B, and trace of row of AB. And so I will denote them by taus, tau A, tau B, tau AB. And in fact, I guess the non-trivial part is a claim that not only is determined, but also they can be arbitrary. And I'm slightly simplifying the truth here. But as I said, this is an overview talk, so morally speaking, that is correct. So this means that really you can identify a character variety of a free group on two generators with triples of complex numbers. So this is a very simple type of an algebraic set. And well, and of course, by the way, notice at least, this is non-trivial claim, but at least notice that these quantities are invariant up to conjugacy, are invariant under conjugacy, because we are taking traces of matrices. In any event, so now let's consider the free abelian group on AB. Then a similar statement is true. Again, each such representation is determined by this triple. However, those numbers, it's not too difficult to prove that those numbers have to satisfy this identity, polynomial identity. And so the character variety of Z2 is the zero set. Well, I claim this is the only identity which they satisfy. So this character variety is the zero set of this polynomial in C3. Again, it's an algebraic set. So now we are in the realm of algebraic geometry. And in algebraic geometry, every algebraic set has an algebra of polynomial functions on it, called its coordinate ring, denoted in this way. This is a very important notion because you have an algebraic geometry, you have a duality between algebraic sets and certain nice commutative rings. What nice means here? Well, it means finitely generated and no nilpotence commutative rings. And in fact, every such ring is the coordinate ring of some algebraic set that determines it uniquely up to isomorphism. So in this case, the character variety, the coordinate ring of character variety is the quotient of this polynomial ring by this identity. Because of course, this polynomial function is tautologically zero on this set. All right, so why I'm talking about character varieties out of sudden? Well, because there's an old theorem of mine with Józef Przytycki and independently with Doug Bullock, which says that if you take R to be complex numbers, A to be plus minus 1, and M to be any three-dimensional manifold, then as you remember, I told you before, a moment ago, that this is some commutative algebra, where you just take product of two knots or links to be just any disjoint union of them. And we ask, what kind of algebra is that? Well, it turns out to be the coordinate ring of the character variety of the fundamental group of M. And I don't remember now if I mentioned this to you, but those taus, which you saw on the previous slide, these are called trace functions. You can in fact define trace function for any element of the group, not just for those three. And so those trace functions correspond to nodes. Okay, so what does morally speaking this means? Well, it means that scale module over, say, this ring is some sort of quantization or Q deformation of the coordinate ring of this character variety. All right, this shouldn't be too surprising because actually character varieties play an important role in quantum field theories, in different quantum field theories, including Chern-Simons field theory. And so, what I mentioned, or I hope to mention before, and maybe I forgot to mention that. Let's just go quickly here. This is integral over all connections, but it turns out the most important contribution comes from flat connections, whatever they mean. And so now I claim that this character variety is really the space of all flat connections in Witten's work for the group SL2C. Okay. And then, since we are on the subject of character varieties, they also play a role, important role in number theory. So in number theory, if you study number theory, then maybe you heard of this topic of deformation spaces of Galois representations, where people study representations of Galois groups into SL2 with some coefficients up to conjugation. So they also study character varieties. And this is, for example, important in the proof of in the Wals's proof of the last Fermat theorem. All right,
sorry,
but
since I think I'm lost in these theorems, or in this theorem, or your theorem together with Przytycki, SM turns out to be something, it is commutative, yes? So why do we call it quantization?
Well, no, it's commutative specifically when A is equal plus minus 1. Because in fact, when A is not plus minus 1, we cannot even define in general multiplication. So, okay, when I say this, of course, I mean here, you know, A is that Q. I should maybe just put A, I should put here, well, yeah, whatever, I can put A equal Q.
Okay.
Yeah.
Just one more question. You said that in this huge path integral, not path integral, integrating overall connections, in fact, the main contribution comes from flat connections. So this space of flat connections is really smaller. Yes, it's finite dimensional.
Correct. Yes.
So,
and now I cannot find it.
So this is how physicists deal with this problem. Yes, they don't care. They only consider this finite dimensional.
Well,
subspace over.
Well, no, they need to care, but you can try to take a limit when k goes to infinity of this, and then it turns out that in the limit, the non-flat connections indeed become insignificant. If you take a limit of k going to infinity, so this q will go to 1, then indeed in infinity, in the infinite limit, yes, it's enough to look at the flat connections. But but unfortunately, this doesn't help us with any of those particular integrals. It tells us something what we can expect in the limit of k going to infinity.
Okay, thank you.
And yes, so this leads to asymptotic conjecture about this invariants, which are still open, at least partially. Okay, yeah. So going back to that, so and okay, so this is a very good question, of course. Thank you, because it's related to what I'm going to say. So now, SU2, so for G equal SU2, the TQFT of Reshnegan-Turayev, well, remember it's supposed to associate spaces to surfaces, and those spaces are very closely related to the Skene modules of what free manifolds? Well, of thickened surfaces. And the Reshnegan-Turayev theory works for roots of unity, so you need to take A at the root of 1. So this is all related to that. And now, going back to Skene modules in general, you know, the definition is quite short, but abstract. So in fact, they are very difficult to compute. As I said, you really, by definition, you are dealing with a quotient of something which is infinite dimensional by infinite dimensional submodule. So it's not easy to present them by generators and relations. However, there's a surprising conjecture by Witten, which was recently proved. And the conjecture says that for any closed manifold, Skene module is in fact finite dimensional. And those guys use high-tech machinery to prove that. And indeed, Skene modules have relations to some advanced topics in geometry. In particular, they can be studied and they are related to certain derived objects in algebraic geometry, derived stacks to be precise, and then conjecture they're related to Gromov-Witten invariants as well.
Sorry, Adam, can I have a question? What is the ring here, CA?
Well, this is the rational functions with complex coefficients and variable A.
Yeah, and something about earlier. So you said that SM is an algebra only when A is plus minus 1?
Correct, yes.
Okay, thank you.
Yes. I'm running out of time, but let me hope at least to say, to cover perhaps this slide. So, so now let's consider an oriented surface sigma, and the free manifold being a thickening of sigma. And then this theory becomes richer, because then actually for any Q, we have a product, okay? And the product is just given by stacking L1 on top of L2. So for a thickened surface, we know how to canonically put two links together, one on top of the other. And this makes this scale module into non-cumulative in general algebra called scale algebra of sigma, and which is denoted by S sigma. All right, so for this ring, this is some quantum deformation that this time is an algebra, quantum deformation of the coordinate ring of character variety. So clearly, I will not be able to cover connect all those connections of this algebra with other objects, but let me just say that these are examples of quantum cluster algebras. So now cluster algebras and quantum cluster algebras are popular and hot topic in algebra. And they're also closely related to something called quantum Teichmuller spaces of Chekhov and of Fock, of Chekhov and Kashayev. In fact, maybe I can even go bolder and say that, in fact, scale algebras are the best, I think, notion of what quantum Teichmuller space should be. All right, and maybe let me try to summarize it just in few words. So Tangle a few years ago extended scale algebras to stated scale algebras, which allow not just loops in thickens in this manifold, but also arcs with their ends at the boundary of sigma. And then there are certain boundary scale relations which are needed to be added. And this leads to a new rich theory of scale algebras, of stated scale algebras. They're called stated because the ends must have a sign plus or minus. And let me quickly summarize what I wanted to say here. It turns out that stated scale algebra of a bigon is in a natural way isomorphic to the quantum group OQ-SL2. And well, the product is given by stacking one tangle or one link on top of another. There is a coproduct here given by splitting a bigon into two bigons. Antipode is can be described geometrically as a rotation, 180-degree rotation. So this gives a new approach to geometric approach to quantum group. OQ-SL2.
Say it again. How do you describe the antipode? Rotation by 180 degrees.
That's right. Yep. So so this gives a completely geometric approach to quantum groups, and in fact allows to interpret certain, I would say, mysterious, abstract notions in the theory of quantum groups geometrically. And what I will, well, let me just say very briefly that I'm just finishing a preprint, a work with Tangle, which frankly, we work on it for the last 2 years. It's quite substantial amount of work, and in which we generalize this theory to SLN, and everything what I said about SL2 can be done in SLN. It's slightly more complicated, involves n-valent graphs, but everything that I stated so far works in that case.
And you really mean the standard Q deformation of SLN groups, right?
Yes.
Wow.
I do.
Maybe you could give a talk at a non-commutative geometry seminar about this.
Sure, I could do it. Yes, I could do it. So I'm out of time, and so I guess I will. It's time for me to stop.
Okay.
Again, thank you for listening and for inviting me.
Thank you very much. Let's thank Adam for his wonderful talk. Okay, there were some questions during the talk, but it's never enough. So if you still want to torture Adam, torment him with questions, fire at will. Adam, why don't you go at Adam?
Oh, okay, I see some question on the chat.
Oh, just
Oh,
thank
okay.
you. This is a thank you.
Okay, I'd like to add some comment and a question. Well, at the beginning, you said that the value of some branch of mathematics can be somehow measured by the way it connects with other branches of mathematics and science. We were talking about the connection of not theory with physics, with topology, but to me the most surprising was the connection with the theory of large cardinals, which which I have thought to be somehow isolated branch of mathematics, maybe because I don't know much about this theory and I wouldn't like to offend anybody who is interested in it. But well,
Excellent question. So I don't have time to elaborate on this. This is whole topic, but you know what? I would say this: no matter what you intend to study, whether you study analysis or algebra, you just have to check that out. So the term to look is lever tables. Read about lever tables, and it's just amazing. The story is quite amazing.
could you please repeat?
Well,
Write
I'm
it in
saying,
chat. Can you write it in chat?
well, you see here on the screen, I wrote the lever tables, and I hope I'm not mispronouncing it. Or maybe I am. Okay. Anybody in the audience who knows what I'm talking about? Because I'm trying to figure out my spelling.
Yes.
My spelling is not perfect.
Well, there is a suggestion. in chat.
Lever tables. Okay. So what I was saying is, even if no matter what area of mathematics you are interested in, read about that, because this is just mind-blowing. Okay. But in general, it's connected to questions about large cardinals. What are large cardinals? Like, well, I don't know. You can ask, what can you ask? Well, you can ask about cardinals larger than that Aleph 0. Yeah, I cannot. I will have to think harder to tell you a reasonable question about large cardinals, and some of them are possibly independent of Solomon or Franklin. Some of them are not. You can ask whether such a large cardinal exists or not. Anyways, this is related to that, and that is related to braiding, and it's very, very weird story.
Okay, I will take a look. Thank you.
Yeah, you're welcome.
So may I ask again?
Oh, sure.
So for a simple-minded person, when it comes to quantum field theory, what is the connection with this quantum field theory understand in the terms of Wickman axioms? This topological one.
Okay, so let me
how
first
this topological quantum field theory relates to the axioms of quantum field theory, the Wickman axioms.
Oh, well, now, so now you stumped me, because I don't know, I'm frankly not an expert really in quantum field theory. I don't know Wickman axioms, but shouldn't they be similar to these?
No, this is a construction of distributions, operator valued distributions. So this is somehow, for me at least, a different flavor, but I'm
So for
definitely not an expert on this.
Yes,
so.
I unfortunately I cannot comment about that. This quantum field theory is topological because many quantum field theories depend on the metric on the space M, and this one does not. But you know, I don't know about Whitnam axioms, unfortunately.
Okay.
All right, anybody else? Anybody else from the audience on site? I don't see any raised hands. How about folks from the Zoom? No raised hands. So in this case, let us thank Adam again for his fascinating talk and exposition of knot theory.
Thank you. Oh,
Now we are slowly coming to an end, so it's time to conclude our meeting. This was the last talk of our school. As they say, all is well that ends well. And I think we can say that Eva and I brought it to a happy end. And I'd like to take this opportunity to thank the Bendevo team for the hospitality. We, at the beginning of the conference, we thanked basically almost everybody. The Banach Center first and foremost, but if you want, Bendevo is part of the Banach Center, a disconnected component if you want. And I must say that the way we were taken care of was quite amazing. Many things went wrong, many things were problematic, but the point is that the problems were immediately resolved. And I think that they went beyond the call of duty in meeting our needs. And in particular, my big fat thank you goes to the IT person, Michał. I forgot his surname, but he is Michał. And of course, to the director of Bendevo, who is Sławomir Malecha. They really helped us a lot. But I think I can say about the whole staff of Bendevo that they really took very good care of us, and we appreciate it. And as a punishment for their good deeds, Eva and I plan to organize the same type of a meeting in about a year. But for the time being, I think the meeting is concluded.
Yes, but let me thank again the students. I mean, there were there was a committee of 6 students who put a great deal of work, and let me recall their names once again. Jakub Krzysztoń, Kacper Mazur, Dawid Migacz, Daria Perkowska, Patryk Prewendowski, and Karolina Stefańczyk. Without their work, nothing would be done.
And I just remembered it was Michał Woroch.
Okay.
Okay. So now we named everybody. Okay, so thank you guys. We can have the high five. The meeting has ended. I stop the recording.